Hi there, and welcome back to Basic Math for Economics. In this video, we need to start talking about matrices because we're going to find they're going to be a much simpler tool to solve more of our complex problems. So the first thing we need to talk about when we talk about matrices is matrix conformability. And we're going to find that matrices have to have certain properties if we're going to do any kind of mathematical operations to them. So anyways, basically, if we want to add two matrices together, they need to be shaped in a certain way. If we want to multiply them together, they need to be shaped in a different way. And by shaping, I mean the number of rows and columns that they have. So let's go over a couple of the conformability requirements, and then we'll do also a few of the mathematical operations involved with them. So the first one that we want to talk about is when we add two matrices together. And that's probably the most straightforward. And this is a pretty strict requirement, but in order to add two matrices together, they have to have the same number of rows and columns. So, and as a quick reminder also, rows go from left to right, whereas columns go from top to bottom. So right here, this matrix that I'm giving you, it has 2 rows and 3 columns. So I like to think of columns as pillars. You know, there's 3 pillars right there. The first column has the elements 1 and 4 in it. The second has 6 and 3. The third has 2 and 5. But rows get stacked on top of each other. I like to think of the rows as seating at a concert or a theater. You know, they are on top of each other. So the first row contains the elements 1, 6, and 2, whereas the second row contains elements 4, 3, and 5. Anyways, if we have two matrices that are additively conformable, we can just add each individual element of the matrices together to obtain our new matrix. So let's actually do that. Let's consider matrices A and B below. I've got A and B, and I want to add them together. Well, to do that, I just add up each individual element. So first I have the first element in the first row and first column is 1 in A and 2 in B. Well, 1 plus 2 is 3. Then the next one, in the first row, second column, 6 plus 1 is 7. First row, third column, 2 plus 4 is 6. Going on, I'm going to get 9, 9, and 8 for my second row. And that's all there is to it. That's a very straightforward way. The important thing, though, is that they have to have the same amount of rows and columns, or else you won't have anything to add when you get to these weird misshapen matrices. And we just can't add them together in that case. In fact, let's actually take a look at that. So let's consider matrices C and D below. So matrix C has 2 rows and 3 columns, whereas matrix D has 3 rows and 2 columns. Well, there's no way for me to add these two together because I just can't work with them. So they are not additively conformable, and there's nothing I can do about that. So yeah, that's it. If someone asked me to add matrices C and D together, I just have to tell them I can't do it because they're not additively conformable. So we got to make sure that's going to work for us. All right, let's move on and talk about multiplying matrices. And again, these are going to have conformability rules as well, but the rules are going to be a little bit different. So before actually we get to that, let's talk about multiplying by a scalar. So when we multiply a matrix by a scalar, which is just a single number, we're going to multiply each individual element of that matrix by the value of the scalar. And for those who don't remember what a scalar is, that's just a number that's outside of a vector. Now, most of the numbers that we have used in our lives are scalars rather than vectors. If it's not in a matrix or in a vector, it's a scalar, and we can treat it specially. But thinking of it like this, if we take a matrix and we multiply it by a scalar, all we're doing is just adding the matrix to itself a number of times equal to the scalar. And that's really it right there. So for instance, if I want to calculate or multiply the matrix A by 3, I'm just adding A plus A plus A, or it's just 3A. I do that, and I'm going to get 3, 18, 6, 12, 9, and 5. I multiplied each individual element of matrix A by 3, and I get my result right here. So that's it. Multiplying a matrix by a scalar is a very simple operation, and we don't really need to worry about it too much. But now let's do multiplying a matrix by another matrix. And the first thing I have to emphasize is that the order of the matrices matters. Depending on which matrix comes first can give us different results. And in fact, the way we order the matrices can actually determine whether we have conformability or not. So anyways, to emphasize this a little bit more, this is different than what happens when we multiply by scalars. You know, we were taught when we were learning basic algebra that 3 times 2 is the same as 2 times 3. That's not the case with matrices. Multiplying matrix C by matrix D is not the same thing as multiplying matrix D by matrix C. So when you get into econometrics and you start deriving the formula for ordinary least squares, I mean, look at the order in which they do things. They'll either do things like pre-multiply or post-multiply in order to get the desired result. And that's really important because it's going to inform what we choose to do. So in addition to the order mattering, the matrices must be multiplicatively conformable. So in order to be conformable in a multiplicative sense, the number of columns in the first matrix must equal the number of rows in the second matrix. And that's our rule right there. They don't have to be identical. They just have to have one dimension and a specific dimension between each matrix that are identical. So let's look at this. Let's go back to A and B. And remember that these two matrices were additively conformable. However, they are not multiplicatively conformable. That's hard to say. So basically, if I take matrix A, multiply it by matrix B, well, matrix A has 3 columns and matrix B has 2 rows. I can't work with that. There's nothing I can do to multiply them together. Same thing. If we calculate B times A, matrix B has 3 columns and matrix A has 2 rows. So there's nothing I can do with that. It just won't work. They are not conformable in this sense. So if I got asked to multiply these two matrices together, I'd tell them I couldn't do it. Let's go on to matrix C and D. Remember, they were not additively conformable, but they are multiplicatively conformable. And furthermore, they're actually multiplicatively conformable in both directions. Now, this won't always happen. A lot of times when dealing with matrices that are multiplicatively conformable, they'll only be conformable in one direction. But we have a special case here where they're multiplicatively conformable in both directions. So we calculate C times D. Matrix C has 3 columns, while matrix D has 3 rows. So that's multiplicatively conformable. If I do the other way and calculate D times C, matrix D has 2 columns, and matrix C has 2 rows. So either way, I can multiply these two matrices together. Let's actually calculate it out. So let's calculate C times D. So the pattern for multiplying two matrices together is the same. Basically, we have to calculate each element of the matrix individually, and the instructions are very kind of complicated. So to get the first row and the first column of matrix CD, we multiply the elements of the first row of matrix C by the elements of the first column in matrix D, and then we add them all together. So that's a bit complicated. It's a big step. So let's just go through it directly. So when we're dealing with the first row and the first column of our new multiplied together matrix, we look at the first row of the first matrix and the first column of the second matrix. Take all of the individual terms and multiply them together. So I'm going to take the 1 from matrix C, multiply it by the 2 from matrix D. Take the 6 from matrix C, multiply it by the 1 from matrix D, and the 2 from matrix C, and multiply it by the 5 from matrix D. So from those, I'm going to get 2, 6, and 10. From there, I take those 3 numbers and I add them together, and I get 18 from that. And that product, or that result, is going to be the first element in my new matrix. So I can do that, and I can repeat the process to find all of the elements of matrix CD. So for example, to get the element in the second row in the first column of matrix CD, well, I use the second row in matrix C in the first column in matrix D. So whenever we're talking about a row, we use the row from matrix C, and whenever I'm talking about a column, I use the column from matrix D, and that will give me the element in the matrix that's multiplied together. So feel free to work through these, but if you work them out, you get every possible combination of row and column, you're going to get the following result. We're going to get the matrix CD right here of 18, 36, 36, and 51. So notice that it doesn't have the same dimensions as either of our individual matrices. This is a 2 by 2 matrix. We're going to find that when we multiply them together, the resulting matrix is always going to have the same number of rows as the first matrix and the same number of columns as the second. So since the first matrix had 2 rows and the second matrix had 2 columns, we get a 2 by 2 matrix. Well, all right, that's it's a little bit complicated, but it's workable. We can get through this one. So what if instead we calculated DC? Well, we can do the same thing. Now we just use the rows from matrix D and we use the columns from matrix C. And this is going to yield the following matrix right here. And again, feel free to practice this one. It's a good exercise in getting comfortable with multiplying matrices together. But we get 26, 30, 34, 17, 18, 22, 17, 39, and 25. But notice that this is a 3 by 3 matrix as opposed to the 2 by 2 matrix we got when we multiplied C by D before. So that's fascinating because not only do we have a different result from matrix CD, like I said, the order matters in this, but we get a completely different structure of a matrix depending on the order of our operations. So remember that when we multiply matrices together, the order matters. Alright, so the last thing to talk about is conformability when we're dealing with an inversion. So we invert matrices quite a bit in econometrics, but in order to be able to invert a matrix, it has to be a square matrix. And a square matrix is just a matrix with the same number of rows and columns. If it's not a square matrix, we cannot invert it. So there are some neat tricks in order to get a square matrix. Those will be taught in your econometrics class, but we can transform any matrix into a square matrix by multiplying it appropriate. We're going to go over inversion in a later lesson. However, there's a couple other tools we need before we are ready to talk about that. So anyways, thanks for watching this video.